Okay, so now this is the third recording for the test review. This is, we're going to do one problem for complex fractions, then we're going to go into inverses. So on a complex fraction, you're going to rewrite the equation into regular form. So you'd have m over 3 minus 1 over 3 divided by, which this is your numerator, which goes right here, divided by 1 minus m squared over 21. So now you've rewritten the problem. Now you're going to do your dot and flip. Since you're dividing here, you need to change it to a multiplication problem. So I have a common denominator here, so I'm going to rewrite this fraction with my common denominator as m minus 1 over my common denominator. Then I'm going to change my division sign to a multiplication sign. Now I get to flip my second fraction. So instead of 1 minus m squared over 21, it's going to be 21 over 1 minus m squared. Now I have a multiplication problem. And I'm going to see what I can factor out and reduce. Immediately I can see that the 3 and the 21 can be reduced. So 3 goes into 21 7 times. So I'm left with 7 times m minus 1. Now I see I've got a difference of 2 squares. 1 is a perfect square, m squared is a perfect square, and I am subtracting. So that's going to be the same as 1 minus m times 1 plus m. Alright, now here's where we do that taking a negative sign out, because m minus 1 is not the same as 1 minus m. M minus 1 is not the same as 1 plus m. But if I take a negative, factor out a negative 1, then that's going to change this to negative m plus 1. And here's what I want you to understand. That if I were to multiply this back out, 7 times m is positive 7m. 7 times negative 1 is negative 7. Right? So here, let me show you. So this would be 7m minus 7. If I were to multiply this out, I would get negative 7 times negative m, which is a positive 7m. Negative 7 times positive 1 is minus 7. So I would end up with the exact same answer. It's just that I've factored out a negative. Divided by 1 minus m, 1 plus m. Now, since I have a positive 1 and a negative m, I can cancel those two out because those are the same thing. And my answer becomes negative 7 over 1 plus m. And that is your answer. So let's cover a couple of the inverses. You know that the inverse of a relationship is basically you're going to switch your x and your y. So when you have a relation 5, 1, the inverse would be 1, 5. You basically are switching your x with your y. Your y becomes your x and your x becomes your y. Then if you need to determine whether the relations below represent a one-to-one function, you're seeing, do they satisfy the vertical line test? Meaning, when I draw a vertical line, does it cross it more than once. And it also has to satisfy the horizontal line test, which means when I draw a horizontal line, does it cross it more than one? So here, this graph satisfies both. So yes, that is a one-to-one function. This one would not satisfy the horizontal line, because if I drew a horizontal line, it would touch it at this point and at this point. So no, there is not a one-to-one function. As well as here, the horizontal line test would not be met. So no, that is not a one-to-one function. Okay? Now, to graph, you're basically going to graph your line, or whatever it is. Here, I'm going to go to my y-intercept, which is 7. 1, 2, 3, 4, 5, 6, 7. Plot that point. My slope is going to be 1 over 1. So up 1 over 1, up 1 over 1, down 1 over 1, down 1 over 1. So here is what this line would look like. The inverse, to find the inverse, you basically switch you switch your x and y, and then solve for y. So I'm going to rewrite this as y equals x plus 7. I'm going to switch my x and my y, so I'm going to have x equals y plus 7. Then I'm going to solve for my y, which means I want to get y by itself, so I'll subtract 7 from both sides. X minus 7 equals y. So now I can graph this line. And if I want to change that back into y equals mx plus b form, I can change that to this. I'd go down 7, 1, 2, 3, 4, 5, 6, 7. My slope is still 1, so up 1 over 1, and graph that line. Now, one thing that we talked about is it should be a complete reflection across the xy axis. So here is, your y equals x. This is your y equals x line. And you'll notice that it is a complete reflection over both. All right, let's do just one more of those. So we've got over here, let's do this one here. Okay, you guys need to remember what to do when you are working with square roots. So, to solve this, to graph it, first of all, you want to put it in your calculator, so you can put in the square root of x plus 3, and then graph it, and there you go. So I don't know if you guys remember. So since this is, if you think about your transformations, this square root graph is the original one started at the origin and went up in a half semicircle or a half parabola. And we can look at this and see that our transformations knowledge can come into place, and that's going to move that graph up 3, 1, 2, 3. And you can also go to the table and plot points, so that I'd have 0, 3, and then 1, 4, and then 4, 5, 1, 2, 3, 4, and 5. It's basically half of a parabola. And since what's inside the parabola has to be positive for it to be a real number, it's only half of it. Because once you start getting underneath the radical and negative number, it becomes an imaginary number. So that is the graph of this function. To find the inverse again, you're going to switch your x and your y. So you've got y equals the square root of x plus 3. You're going to switch your x and your y. X equals the square root of y plus 3. To solve that, you want to isolate your radical first. So you'd subtract 3 from both sides. X minus 3 equals the square root of y. Then you would, since this is taking the square root, you need to square both sides. So you'd raise this to the power of your index, which in this case is 2. So I'm going to get x minus 3 squared, and the square root of y squared is just y. So this becomes my new graph. So when I plug that in, 2x minus 3 squared, and graph that. There's my first graph, there's my second graph. Now, your domain, so I can look at my table and look at my, when x is 0, y is 9. Oh, that would be this way. 1, 2, 3, 4, 5, 6, 7, 8, 9. When x is 1, y is 4. When x is 2, y is 1. I'm looking at the second white. When x is 3, y is 0. And then on up. So here is the inverse. And you would notice that it would be exactly reflection across your y equals x. Okay, so now we're going to see which of these, whether or not they are inverses of each other. And the way that you do that is you basically are going to plug in trying to decide if I should do this one or not. You're basically going to say, does f of g of x equal x? Or does g of f of x equal x? If the answer is yes, then they are inverses of each other. So let's see, does f of g of x equal x? So we've got f of x is 1/2. There's where my x would go, to the third power minus 2. So, since I'm finding the f of g of x, I'm going to plug g of x in for the x here. So, the cube root of 2x plus 4. Now, when I take the cube root and take it to the third power, that's basically going to go away. So, just like you know that the cube root of x cubed would equal x. So when I take this whole thing to the third power, I'm left with 1/2 times 2x plus 4 minus 2. So now when I distribute my 1/2, 1/2 times 2x is going to give me x. 1/2 times 4 is going to give me plus 2 minus 2. X plus 2 minus 2 equals x. So yes. they would be inverses of one another. All right? And then if you were to do the same thing with your g of x, we'll just go ahead and work that problem as well. If you have g of f of x, my g of x is the cube root of 2 times x plus 4. And for this, we're going to go ahead and insert 1/2 x to the third minus 2. So underneath here, I'm going to get the cube root of, if I distribute this 2 to both of these, I'm going to get x to the third minus 4 plus 4. Then when I have combined these, I'm going to end up with x to the third, the cube root of that, and the cube root of x to the third equals x. So, yes, those would be inverses of each other.